Today we look at some definitions and are slowly leading towards the definition of a derivative, which is sort of the main thing of the first thing you study in calculus. So, some definitions. A secant line. If you would have a parabola and you would have 2 points on that parabola, the line joining those 2 points that cuts through that parabola is called a secant line. Now, we don't often talk about secant lines. Did you talk about them in grade 9? When you had a chord in a circle, did you actually call the line that would have continued a secant line? I'm not sure. You would have talked about tangent lines. Yes. Here is not a bunch of stuff, one thing. Just one thing. A tangent line is a line that touches a point, a curve at one point. So here's our parabola again. It touches at one point and usually does not cut the line at that point. So for example, this would be the tangent at that point, and this would have a tangent touching that point only at one place. We would not, even though I could cut through it perfectly only once by going straight up and down, this is not a tangent. There is a situation where on an x cubed graph, the tangent does cut through the curve at that one point. And sometimes, for example, if I took another point on this and drew the tangent there, it does cut through the graph again, but that would still be a tangent at that point. So it's not cutting, it's trying not to cut through that. It's sort of the line that touches it only once. Now, when we figure out the slope of a line, we have two different types of rates of change. We're going to look at an average rate of change, and we're going to look at an instantaneous rate of change. So for example, let's say you're driving somewhere. Let's say it takes, how far from here could you get in an hour? If we're driving, do you think we could get Portage La Prairie in an hour? Yeah? Portage La Prairie is about 75 kilometers away. And so if it takes us an hour to drive from here to Portage La Prairie, our average speed would be 75 kilometers per hour. But do we actually go 75 kilometers per hour the whole way? Do you hop in your car and boom, instantly you're going 75 kilometers per hour, and you go through all the red lights and you don't stop, and then people get mad at you on the highway because you're going so slow, but then you get into Portage and just run over everybody and get there, and the whole time you're going 75 kilometers an hour? No. If you looked at my speedometer on the highway, you'd probably notice it was a little bit higher than 100. I tend to stretch the speed limit a little bit. And while I'm in the city, sometimes it would be 0, sometimes it's 80. Got to be careful in Headingley, that's 70 there, so you can't go too fast, otherwise you're going to get a ticket. So your instantaneous speeds are what your speedometer is saying every time you look down. Oh, now I'm going 110. Maybe I should slow down a little bit. Right now I'm going 30. The average is this, if you say, well, I took 1 hour and I traveled 75 kilometers, so my average speed is 75 kilometers per hour. So we represent rates of change as a bunch of different things. And you've seen already slopes with lines. Lines have slopes. Rise over run. That's a rate of change. How much one thing changes with another. Okay? Another word for slope is gradient. And some more symbols. Have you seen this triangle symbol before? What does it mean? Change. Change in y over change in x. Okay? And when we're looking at that change in y over change in x, another thing that we use to represent that rate of change is the first derivative, which we can write as dy dx, and we'll learn some other notations for it as well. All right, so we are going to make up a story. Let's see, we're going to put time down here. We'll figure out the units. And here, we'll say this is distance from home. You're wanting to go somewhere. So we're going to put up to 5. 1, 2, 3, 4, 5. And should we use our time? Let's do hours so we're not driving too fast. And then here, let's go by tens. Are we driving? Should we go kilometers? Or are we running? Should we go meters? Maybe we're running and let's go kilometers, just for fun, right? Can you run 10 kilometers in an hour? Oh yeah, that's no problem. Can you run, how many kilometers can a person run in an hour? That's a good question. What is like really fast? Okay. You're going for a run. And if we're going to say 10 kilometers an hour is no problem. And so you start off slow, then you got a hill, so you go a little bit faster, and you get to 10 kilometers in 1 hour. And then, yeah, let's have some fun. The next hour, you like sprint and go 20 kilometers in an hour, at which time you like become exhausted and faint and you actually pass out for an hour. There we go. Just on the side of the road, wherever you're running. You've been passed out for an hour. Okay? When you awaken, okay, you all of a sudden realize that you had left a frying pan full of oil on high heat on your oven, and you're really scared your whole house is going to burn down. Probably it would have burnt down already 3 hours later, but all of a sudden you're like, oh no, I have to run home. And you manage to run home 30 kilometers in 1 hour. I think that might be really fast. Okay? All right? You live out in the country, far away from a city. You get home. Luckily, only half your house is burnt down. But you put the fire out, but now you're so exhausted from running and the smoke inhalation and stuff that you have to get rushed to a hospital. So someone takes you in a car and drives you away. So we've got a story, and we've got a graph that sort of represents this story. We have a couple of things that we could look at. Okay? What is the average rate of change from 1 to 3? Well, from 1 to 3, our slope would be a rise of 30 in 3 hours. And so our average rate of change would be 10, and if we add the units, kilometers per hour. Even though we've been passed out for a whole hour on the side of the road somewhere from running so fast. From 1 to 4, though, our rise is 0, right? Okay? And so after 4 hours, if someone came to me and said, oh, kilometers per hour, someone came to me as I'm exhausted just from running home to stop my fire, they're like, oh, your average speed was 0 kilometers per hour. Good job. You're like, because you just ran home. But your average speed at that time is 0 kilometers per hour over that amount of time, because you have got back to where you started from, right? You've traveled no distance. This is one of the reasons I find it really hard to go for a run, because you leave your house, you run, and you end up back at your house 30 minutes later. And I'm like, I could have got here a lot quicker if I just stayed home. So I have a tough time. I like playing a sport much better. There seems to be some sort of purpose, but for a run, just to run to get back to where I started from, I don't know, I guess I should try to find a different motivation there. So I have a tough time going for a run. If I'm late for something and I have to get from point A to point B as fast as I can, and all I've got are my legs, then I'll run. And that seems to work, but otherwise. And finally, from 4 to 5, now our slope from 4 to 5, our rise is 50, and our run is 1, so the average speed over that time is 50 kilometers per hour. Notice that we would have, if I would have found the average speed from 3 to 4, my slope would have been negative, and that negative sign just meant that I'm returning back home. Now, you can't actually have like negative speeds, but the negative adds a direction to it. So these are all averages. But if I was wearing some sort of fancy technology, maybe some sort of Fitbit or Apple Watch that calculated my speed, the instantaneous speed would be what I would look down on my watch and see how fast am I going right now. Do they have that on watches? I mean, they have it on GPSs. I guess you could just strap a big GPS to your forehead and it would have your speed on there. So an average rate of change between 2 points is just finding the slope, the straight line between them. And for a lot of the example that I did, I used a lot of straight lines, so we could find actual instantaneous rates of change or instantaneous speeds just because they were straight lines. But sometimes we deal with curves, and we want to figure out how fast is something going, or what is its rate of change at a specific point. And how could we tell that if the graph is curved? So to find that instantaneous rate of change is finding the slope of a tangent. And the idea for finding that uses the idea of limits. So I've got maybe part of a parabola here. And I've got 2 points on my parabola, A and B. And if I found the slope from A to B, it would give me my average rate of change from that time. And I've got an applet set up here for you of that situation. Oh, A and B are mixed up. Here, whoa, easy. Whoa. Okay, I have to go to my computer. So on our graph, we had A at the bottom, B at the top. Here, I'll put A at the bottom, B at the top. Whew. Saved. Now it's all going to make sense. Are you ready? So if I move B closer and closer and closer to A, okay, can you see that the blue line is getting closer and closer to the green line? So if I put the 2 points really close together, like I have right now, then my secant line is a good estimate for the tangent line. And if I move them even closer, oh, look at that. I can zoom in and move it even closer. It's an even better estimate. So I'm like, oh, if that's a better estimate, zoom in again and move it closer. I'm like, that's an even better estimate. So what could I do? Zoom in again. Now I could do this all class. I'm sure you would get bored even more than you are already if I did that all class. But we could just keep zooming in and getting closer and zooming in and getting closer. And the closer we get those 2 points together, the more our tangent line becomes, our secant line becomes the same as our tangent line. It becomes a better and better estimate. Now how does that show up in the mathematics? Well, if I wanted to find the slope of my secant line, it's just rise over run. So my rise are just subtracting my y values. F of x is my y value for b. F of a is my y value for this point. There it is, f of x minus f of a. That represents the change in y. And x minus a would represent my change in my x values. Formula number 1. If I want to find the slope of the tangent as x gets close to a, I can make a limit saying I want my x value to get close to a. If I do that, what happens on the bottom? Currently dividing by 0, which is not allowed. But if we use our skills that we've learned so far with limits, maybe we can evaluate this limit. And if we can evaluate this limit, we can find the actual slope of the tangent line at that point. Okay. Find the slope of the tangent and the equation of the tangent line to this curve, so that's a parabola, at the point 2, 1. So just drawing a little picture off to the side. We have the point 2, 1. We have a parabola. I'm trying to think if this parabola opens to the left or opens to the right of this. If I plug in 1, I think it looks like this. With a vertex at 1, -2. There's our parabola. What we want to do is we want to find at this point the slope of this tangent line and what the equation of that tangent line is. And we're going to use formula number 1, which says our slope of our tangent line is going to be the limit as x approaches a of f of x minus f of a over x minus a. In our situation, we want it to be at the point 2, 1. So we can say we want to find the slope will be the limit as x approaches 2, because it's going to get really close to 2. of f of x, and f of x we can plug in our entire equation, which is 3x squared minus 6x plus 1, minus f of 2. Does it make sense that f of 2 is equal to 1? Over x minus 2. What's the problem with plugging in 2? Right now, we divide by 0. So we have to use our algebra skills. Can we manipulate this equation so that we can cancel out that x minus 2 and actually evaluate this limit? So whenever we're showing our work with limits, we have to write limit as x equals 2 all the time until you're able to actually plug in that value of 2. Can you see on the top, I could simplify the top a little bit? 1 minus 1, this will just become 3x squared minus 6x. And on the bottom, I have x minus 2. So that was good. That simplified things a little bit. Any ideas? Factor out a 3x out of the top. So our slope will equal the limit as x goes to 2. And if I factor a 3x out of the top, oh man, isn't that nice? That is very nice. And what does that mean? That means that our x minus 2's cancel out. And now can you evaluate the limit? You can just plug in 2 now. 3 times 2 is 6. And so we can tell that the slope of that purple line is 6. A little bit of review from grade 10. To find an equation of a line, we want to find the equation of that purple line. You always need 2 things. You need the slope, that's thing number 1, and you need a point. That's thing number 2. For our purple graph, we just figured out that our slope was 6. And our graph told us that it went through the point 2, 1. That's where the tangent goes through. So we know that our point is 2, 1. Once you have a slope and a point, there's 2 methods for finding your equation of your line that you could use. So I will remind you of both of them. Can I make this a little smaller? Move it off to the side. There we go. How many formulas do you know for the equation of a line? What's one of them? Y equals mx plus b. How many people y equals mx plus b is the first formula they think of? Okay. So we'll do that as method 1. If you think of y equals mx plus b as your first formula, you can take your slope and plug it in for m, and take your point and plug in your point for x and y, which leaves you only with b that you don't know. If I simplify this, I get b is equal to -4. So that means the equation of my line is going to be 6x minus 4. That's using y equals mx plus b. That's called the slope-intercept form of the equation of the line. Do you remember any other forms of the equation of the line? Y subtract y1 equals m subtract m times x subtract x1. Okay, this is slope-intercept. This is called the slope-intercept form because it has a slope and an intercept, the y-intercept. This one is called the point-slope form. Did I do that? And you guys didn't let me know right away? You just let me suffer here? Do you ever do that? Make mistakes like that? What did I do? The y is 2. No, the y is 1. And I plugged them. So this should have been the nice thing about a smartboard. Not the nice thing about your notes if you were using a Sharpie, I'm sorry. Okay, the y is 1, the x is 2. Moving this over tells us that b is equal to -11, and, well, it's not that bad. Whew. And you get 6x minus 11. We would have noticed that because I would have done the second method, and then all of a sudden we would have got different answers, and then something would have been bad. But thanks for noticing that early. This point-slope form just says you plug in your slope where m is, you plug in your y value, watch this, right y value, nice, and you plug in your x value. And now if we rearrange this, add 1 to both sides, you can notice that these equations are the same. So let's look back at this whole thing. What did we all find out? Well, we had a formula that says if we take the limit as x gets close to a, which is dragging that secant line closer and closer and closer until it becomes a tangent line, we can find the slope of that tangent line. Once we've got that slope, to find the actual equation of the tangent line, you can use your grade 10 math about lines, which means you need to have a slope and a point. And then you have a choice. You can either use y equals mx plus b, or y minus y1 equals mx minus x1 to figure everything out. So here's one for you to try. Okay, I still want you to use that first formula. If you've already learned derivatives, you're not allowed to use them. Formula. Able to put the formula in and then factor things out to get a slope of 4. Should be like, okay. All right, some sound effects for later on. And then once you've got your slope of 4, you've got your slope and your point. So then depending on which method you used, you got y equals 4x minus 1. Excellent. Good? So we use that equation to get our slope, and then we use our slope and point to find the actual tangent line. Now, our initial, if I go back to our initial diagram, this was our initial diagram that we used, and we used this x minus a for our run. Okay? Another way of looking at the exact same thing, here I'm going to go, no, sorry. Here we go. Another way of looking at the exact same thing would be to say, I want to make this distance h. Instead of having two values and doing x minus a, I could just call this h. I still have my same point here, a and f of a. But now my point up here would be a plus h, if this distance is h. And my y value would be f of a plus h. Can you see that it's the same idea, just using different variables? Before, we had x and f of x, and we called this x minus a. Now we're defining this to be h as an actual length, and then this point would be a. This x coordinate is h to the right, so it would be a plus h. And my y value is f of a, and now my y value is f of a plus h. So my slope here is the same idea, rise over run, but now we get f of a plus h minus f of a all over just h instead of x minus a. And if we wanted to find our slope, well, now it's the limit as h goes to 0. And this is a typo. This should be h. So if you still have a 0, did I fix it on yours? No. And this is formula number 2. Yes. Yes. Although if I want you to do a specific formula, if I want you to use formula 1, then I'll give it to you in the question. If I want you to use formula 2, I'll give it to you in the question. I won't say no formula 2 and you have to remember which one's which. Okay? But yes, and this one is closer to what the definition of the derivative that we're going to be looking at next. So it's sort of, both formulas mean exactly the same thing. One had a limit as x went to a, and this one has a limit as h goes to 0. So how does this formula work to find the equation of a line? Well, we'd start doing the same thing. To find an equation of a tangent, you need a point and a slope. We already have the point. We need to find the slope, and now it's going to be the limit as h goes to 0 of f of x plus h. So I'm going to write out the formula first. F of x plus h minus f of x all over h. And so for our example, what does function notation mean to have f of x plus h? That means wherever you have an x in your original function, you have to replace it with x plus h. So I'm going to write square brackets here. F of x plus h would be x plus h squared minus 4. Minus, and f of x is just x squared minus 4. All divided by h. Does the notation that I went from here to here and here to here make sense? F of x plus h is just your original equation with the x replaced with x plus h. And f of x is just your original equation. And now we have to use our algebra skills to do mathematics to get rid of that h on the bottom. Any suggestions of something we could do? We could expand the x plus h squared. So what would that mean? Right, this is equal to the limit as h goes to 0. x plus h times x plus h is x squared plus 2xh plus h squared minus 4. And if I distribute the negative here, I would get minus x squared plus 4 all over h. Anything we can simplify? Yes. We've got 4 and minus 4. That'll be 0. We have x squared and minus x squared. That'll be 0. And so in the top, all I'm left with is 2xh plus h squared. On the bottom, I have an h. Now we have a common factor in the top. We can factor out the h. Leaving us with 2x plus h on the top, h on the bottom, and finally, we cancel out that h. Plug in 0 now, and the limit is 2x. Okay? But when are we specifically trying to find it? At the point 3, 5. I probably should have plugged in x equals 3 right from the beginning, but I didn't. So we actually did a little bit fancier math than we needed to. So when x equals 3, the slope would be 6. Now I chose in this time, because we're finding it at a specific point, I chose to plug in x equals 3 at the end. You could have, if you wanted to, you could have plugged in x equals 3 right at the beginning and done the same thing. So you have that choice. So sometimes I've done it where I plug in f of 3 plus h minus f of 3 divided by h. What I've done here is more typical of what comes up later when we use this as the actual definition of a derivative. So now that we have our slope is 6, we know that our slope is 6, we know that our point was 3, 5. I'll just do one of the forms right now. Plug in our slope. Y value is 5. X value is 3. And we get our equation to be 6x minus 13. So now I'm going to start off this next one for you right here. Okay, I'll show you that much. We've got the square root of x plus 3. And in this time, I'm going to start off by plugging in the x value right away. So our slope formula is the limit as h goes to 0 of f of x plus h minus f of x over h. And since I know that my x value is 6, I could plug that in right away. And this 3 is equal to f of 6, so I could plug that in right away as well. So this is different than what I did last time where I plugged it in later. And then I've given you the hint in green that with square roots, you often have to multiply by the conjugate to make things work. So I'll give you this much, and I'll ask you to finish it up. I'll scroll down so you can see the rest of it to see how you did. After multiplying them out, everything nicely cancels out. Notice on the bottom, one of the things, I multiplied out the numerators, but I didn't multiply out the denominators. I wanted to keep this h factored out, because that's the problem, right? That's the thing that we want to cancel out. And we can see here that after I do 9 minus 9, the h on the top is all that's going to be left. Will cancel out with the h on the bottom, leaving me with only a 1 in my numerator. And then my slope is 1/6. And then depending on which method you used, you will get your equation to be 1/6 x plus 2.